people and you can see me and we can be all there. Does that work?
Yeah, sure.
Okay, so with that, let's get started. It's my pleasure to introduce Ben Bogin from Tel Aviv University. He's a final year PhD student with our good colleague, Jonathan Berant. He's done a lot of exciting work in semantic parsing, text to SQL, and so on, and more recently on understanding the difficulties of compositional generalization that all our models face and how to overcome them. So looking forward to your talk.
Okay, thanks, Ashish. So thank you for having me. I'm really excited for this talk. So I will talk about understanding and improving compositional generalization. Feel free to stop me if you have any questions, any clarification questions maybe, and then towards the end we'll also have more time. So let's start. So you might agree with the saying that NLP is doing relatively well these days. So basically, if you have some task that you care about, you collect label data, you fine-tune some pre-trained model on it, and well, in many cases, you will get good performance. And even you don't really have to fine-tune a pre-trained model anymore. If this model is large enough, you will just use in-context learning. But I mean, this is of course not really the case, and you also have many cases for which you don't get good performance. And one of these cases is out-of-distribution data. So there's a lot of examples for out-of-distribution data for which models can't generalize very well to, for example, unseen domains and unseen tasks. And what we're going to talk about today are unseen compositions, or what we call compositional generalization. So before I'll show you this slide about compositional generalization and how we can define it, so I actually have this nice conversation that I had last week in the Knuckle conference. So I was talking to someone and he was asking me the usual conference question of what are you working on? And I said compositional generalization. So he asks me, I know what each of these words mean, but I'm not sure what they mean combined. So I looked at him and said, yes, this is exactly it. It was kind of nice because compositional generalization is exactly the ability to understand and produce unseen combinations of known concepts. So for example, if you know what a winged insect is and you know what a giraffe is, then it will be easy for you to imagine a winged giraffe. And compositional generalization is relevant in many tasks and setups. So for example, in the visual question answering, you might want to test your model on combinations of reasoning skills, for example, the quantifier all and the operator and you will test this model on examples that combine these reasoning skills, even though they were never seen together. We can do the same thing with open domain question answering. So for example, or actually, again, you will test your model on these combinations of unseen concepts. And also for semantic parsing, which we can define some example for what a compositional generalization setup would look like. So in this case, we will split all of our data such that all of the atoms will appear in the training, but the test set will include some structures that did not appear during training. So for example, we can see here our task is to translate utterances into an executable logical form. And we see here that during training, the model can observe these different operators, for example, equal and or. And then during test time, for the first time, the model will see some unseen combination of these operators. Okay, so why do we care about compositional generalization? I guess that the main reason is that it's important for trust. If you want to build systems that users can trust, then of course it should be able to do this kind of generalization. Since if a user knows that a model can do some skills A, B, C, and so on, and it knows that it can combine these skills, then it would expect, the user would expect that the system would work with any kind of combination. and not just the specific combination that we're seeing during training. And from the research side, then we can define this problem so that it will be well defined in many different tasks and contexts, and humans can do this very easily in most cases. Okay, so you probably saw this coming. So we know that NLP models struggle to compositionally generalize, and this has been seen in multiple papers over the last few years. And you can see on this chart, for example, the generalization gap between an IID split, where we just randomly split the data into training and test sets. And so this is the lighter blue. And in the darker blue, we have accuracy of models on compositional splits, where we split the data in a more challenging compositional way, such that the test set includes unseen structures. And as you can see, this gap is very large. Okay, so now this will be the structure of our talk. We will see how we can approach compositional generalization within 3 very general NLP paradigms. And we'll start with the most task-specific paradigm to the most task-agnostic one. And so the first way to approach compositional generalization is by using some specialized architecture or some changes to the architecture that we believe will allow the model to be more compositional. And basically here we use some inductive bias that we put into our model or into our training system. And we use this to encourage compositionality. And the nice thing about this is that in many cases, it works. That is, these models can generalize pretty well into unseen distributions with unseen compositions. And also, as we will see next, one example for it can also be interpretable. So if you have this compositional inductive bias in your model, then you could see all the different compositions that the model does and get improved interpretability, which is, again, important for trust. However, the downside for this approach is that in many cases, this is too specific to the task that we designed this architecture for. And also, in many cases, these models are not pre-trained. And so, as we now know, it's really not as applicable to the very variety of NLP tasks that we maybe care about. So that's one approach. And the other paradigm is this very commonly used setup. Yeah.
Could I just ask, could you give an example of the specialized architecture that you have in mind?
Yeah, sure. So I'm going to talk about our model with grounded latent trees, where we parse the model into a trees. But also there are a few other examples. So for example, Jonathan Herzig from a group also did something very similar with parsing to trees for semantic parsing. And we're going to talk about visual question answering setup for the specialized architecture.
Awesome, thanks.
Okay, so one other paradigm that is very commonly used is where we take a pre-trained model and we fine-tune it. And this is very simple, and we have this pre-trained model which can generalize to a lot of setups, but in the compositional generalization splits, we will see that we get very limited generalization to unseen structures. And while there are quite a few methods from recent years that have tried to improve this, we will actually not talk about how to directly improve it, but first we'll try to understand why and when this happens. And we'll try to really characterize when do models have a hard time to generalize to these unseen structures, and then we will see how we can leverage this insight to improve generalization.
Hey, Ben.
Yeah.
We'll just switch the camera to that, and then you can just turn the laptop, continue as you.
Oh, okay.
Yeah, and then you can just face this way. And, yeah, there we go. Then we turn this around. Yeah, awesome.
Yeah, that should be better.
Perfect. See people.
Yeah, that's
Sorry,
more
yeah,
more
Ben can
natural,
actually
right?
see you guys if you have your cameras on. That's great.
Okay, yeah, that's better. Okay, so yeah, I was talking about pre-trained models which we can fine-tune. And finally, for the next paradigm, so, and again, this is very common these days, you take this large language model which you don't fine-tune. And as we know, these models have a very impressive ability to generalize. And if we test it on unseen compositions or in the compositional generalization setup, we see that indeed we get improved generalization with no gradient-based training at all. And this is very impressive, of course. But then again, it is very far from being perfect. And not only in the compositional generalization splits, but also in the IAD splits. So where you can fine-tune, if you can fine-tune your model, then you might get lower compositional generalization abilities, but still you can teach your models a lot of the different things that you expect in your data set. So now if you can't do this, then you're a bit more limited in the ways that you can improve your model, since now you don't do any fine-tuning. So we'll also talk, basically we will now talk about each one of these three paradigms, and we'll see some instance and some examples for what we can do or how we can understand better the problem. Any questions so far? Okay, so let me start with a specialized architecture. And first, I will ask, why do we actually care about specialized architectures? And I will say that I guess that the reason is that we have these very expressive models, transformer models, but still there is no explicit alignment between the input and the computation. So you might get this very long and complex question, which requires multi-step reasoning, such as what is the shape of the large thing that is on the right side of the metallic cube and left of the green sphere? And basically what we do with an expressive model such as transformers, we basically have this very complex learned function, which simply outputs the answer cylinder. And while it works in many cases, still this is very sensitive to changes in the way that the question is structured. And so that's one of the reasons that these kind of models fail to generalize on unseen structures. But if you will have explicit alignment between the input and computation, then we could expect this to work better on generalization setups, and also we will gain better interpretability, as we will see. So with that motivation in mind, we've designed the grounded latent tree model, where basically we parse the question into a tree, and at each intersection of the tree, we ground this intersection or the span that it covers into the image, into the objects in the image, and into some compositional representation. So as you can see here, we get this long question, and we can see exactly the way that it parsed and the structure of the different reasoning step that the model does. And important to say, we see here this one tree, but it's just for visualization effect. But in fact, everything here is soft, and a lot of trees are computed to get to the answer. And this is important from the training side, since we can basically, since the trees are latent, we can use this, we can train this model just using the input and the denotation alone. So in very high level, how does this model work? So basically, we compute a representation and a denotation for each span of length 1, which is basically each token or word, and then we recursively compute this representation and denotation for length 2, 3, etc. We basically do something similar to the COVR algorithm. And then, since we do this recursively, we end up with having a representation and a denotation for the entire sentence, and we can predict the answer. And this is, again, as I said, it's trained only with denotations, and the tree structure is learned entirely during the process without any supervision. Yeah.
This clarification is for the, are you assuming some kind of a parse done on the tree?
No. So we don't use any parser. The parsing is built in. Yeah, so I didn't really have this in the slide, but basically, so for example, in the box, in the upper box, we will compute all of the possible splits. So it could be same color as with the tiny shiny sphere, but we'll also compute something wrong, such as same color as the tiny shiny and sphere. And then basically the model will learn which one is better.
And do you have denotation supervision for every span?
No. So the denotation is only for the last, only for the question.
The
Basically.
full thing, okay.
Yeah. So everything is learned. Everything here is latent and learned from denotations alone.
And Ben, it seems like you have. Oh, so actually, if you go to the next slide, it looks like you have rules that allow you to skip over things. So these Greek letter things.
Right. Yeah. So I didn't go into the details, but basically at each intersection of this tree, so the model both has to make some decision. So one will be which object. No, actually, okay. So before that, which of the splits am I going to choose? Softly, of course, and then it's going to choose which kind of operation it's going to do. So we have both these hard-coded operators that we saw were useful, such as intersection and union, but also this more general function that can be learned, which is, so here you can see this with the I function, which can do just anything. And this is useful, for example, for functions such as same color as. So you can see, let's see. Okay, also in front of tiny green metal objects. So we will have this function that we did not hard code in any way, just learned how to do this. But also we have these hard coded operators such as union and intersection, and also a skip operator. But I will also say that this model works perfectly without any of the hard coded operators. It just becomes less interpretable. Okay. Yeah, so I was going to say, as you can see, the output is very interpretable. You can see exactly the grounding from each word to the image, and then from each intersection again to the image, and you can see the entire process of operators that were performed. And this really helps to gain trust, so we can kind of tell if this model makes sense with what it does. And yeah, so if our main motivation is to improve generalization, that we see that indeed this is the case both in the IID split and in the compositional split, where we have these new structures of questions. And in both cases, we get nearly perfect results. I will say that this, yeah, I removed this slide, but so this is COVR and closure are synthetic data sets, but we've also tested our model on natural language, the natural language version of these data sets. And again, we get really good generalization accuracy. Okay. So, yeah, I don't have any clock in front of me, right? Oh, 10:20. Yeah, so we're fine.
Bhavana has a question.
Hey, Ben.
What?
Bhavana.
Oh, yeah.
This is Bhavana. I have a question regarding specialized architecture part that you just covered. So this is really cool that you can semantically parse and come up with a soft representation over the objects in the scene, which is what the clever dataset focuses on. I'm curious, is there any way to answer questions that require common sense knowledge in this setup? Even though your attention is softer over the objects, it has to be about what is given in the input, right? Can you apply some external knowledge, like which object can be picked up by a magnet, for example, in the same case?
Yeah, that's a super interesting question. So I guess our focus in this work was about how we can parse and latently ground different intersection in the tree to an image. And definitely, I would say that you can change the kind of operators that here work on images to be something that maybe work on these knowledge graphs, or just some common sense that the model would know, and then gain this interpretable output also for these kind of questions. Yeah, that would sound something really interesting to try.
Thanks.
Yeah.
Hey Ben, Tushar here. So am I correct in understanding that the only inductive bias that you're using is the fact that it is a tree structure? Like there is no supervision on green should map to these objects, or you should map to a syntactic tree, or union only applies on these kind of inputs?
Yeah. We don't use any supervision at all except from the answers, and the inductive bias is the way that we get to these denotations and representations in a compositional way.
Got it. Do you have a sense of why it learned something meaningful? Like it's interesting, but it's curious also, right? Like it could have learned something completely unintuitive to still get
Yeah. No, that's a really good question. So I'm showing here results on synthetic questions. So the model has seen all kind of these examples, and it's actually quite big. So I don't know, maybe it makes more sense that it looks that perfect. And so I don't have this here such a slide, but you can see it in the end of the paper where we give examples for natural language questions. And then you see that sometimes things are perfectly interpretable, even for these operators that weren't seen in the original dataset. For example, negation, so it does this really well, and the parsing looks really nice. But then, yes, sometimes, of course, it's not perfect, and it might still get the answer right, but just with the wrong tree. We've had some experiment trying to quantify. It's an experiment with humans where they basically try to rate how much this interpretable output helped them with understanding the output. So in many cases it works, but definitely not always.
Cool.
Is maybe an important aspect that there is some sort of curriculum learning, that there are a lot of simple examples in the data set, like the green metal sphere or the green sphere, and then it has an answer for that, and so it sort of learns by sort of those very simple examples. It starts to ground these substrings. Or is the data set only these complicated examples that are compositional? Does it have the sort of atomic examples in the data set?
Yeah. So some questions are, I mean, we didn't explicitly do any curriculum learning, but some questions are easier, and yeah, it helps the model to learn the basic grounding. And I think these were the things that we saw pretty early. I mean, it's one of the easiest things for the model to learn is like the grounding of the different words, and then it's this learning how to combine them together was more challenging. Okay, so now let's move on to, we talked about specialized architecture. So it has these really nice advantages, but again, it's not pre-trained, and it's hard to maybe use this for the more general setups. And so with this in mind, let's continue to this next paradigm where we fine-tune pre-trained models. And so this setup is really common. You just take a pre-trained model, BART T5 or whatever, and you fine-tune it on the training set that you have. And then in this setup, you will test your model on examples that contain unseen structures. And so we've seen that we have this large generalization gap between an IID split and a compositional split. And there have been many methods to improve generalization, such as supervising attention, data augmentation, meta-learning, scaling the amount of data, etc. But actually, I'm going to take a step back and to think about what's exactly going on here. I mean, there is this perception that models categorically fail in compositional generalization. That's why we see all of these papers saying that models can generalize. Even I said that before, but actually this is not really the case always. So models can generalize well sometimes. So for example, here we see two data sets. So one is the COVR data set, which I'm going to talk about in the next slide. And we see here all of these kind of manually defined splits for which models can generalize on some of them, but not on the other. And the same thing happens in the COGS data set by Kim and Linzen, where they show that some splits models generalize to, but not on the other. So I will quickly say a few words on the COVR data set. So COVR is a VQA generalization benchmark, a compositional generalization benchmark, where we have questions with up to 5 images that require all kinds of reasoning skills. So for example, in this question, it's actually an utterance, no men are surfing on a white surfboard. And the answer is true, since, well, there is no man that is surfing on a white surfboard. But notice that we carefully, I mean, we do this automatically, but we've carefully designed this process so that we will have good distractors. So for example, we do have here a man holding a white surfboard and a man surfing on a red surfboard. And we do this to prevent these kind of shortcuts that we see that models learn how to do. And so COVR contains a complex question with higher order operators, quantifiers, and aggregations. It mitigates reasoning shortcuts, as I've just seen with the example with the surfboard. But in our context, what's useful here is that the high number of program templates allow to create and evaluate different compositional splits that we can think of. So let me show an example for 2 of these splits. Here we see that the model never sees the quantifier all together with a complex scope. So for example, the model will see in the training set, all birds are black and all chairs are wooden, but it will be tested on an example which is more complex, such as all computer mice that are on a mousepad are black. But note that during training, it does see an example for such a complex scope, just not with the all operator, but with the no operator or none. And here we see that this pretty strong baseline just didn't generalize very well on this split. On the other hand, this different split where the model never sees count together with an attribute. So for example, it will see there are 3 dogs, and it will see what is the black dog holding, and it will be tested on there are 3 black dogs. So here actually the model generalizes pretty well. And it's kind of unclear to understand what's hard and what's easy. And that's exactly what we had in mind with this project that I will next show. We have this question, and I'm coming back to the semantic parsing setting, where we really want to understand what are the conditions under which compositional generalization occurs in sequence-to-sequence modes. So again, this is a semantic parsing setting. And we can define this as a more, as a question that you can actually define well, which is, can we predict if a specific test instance will be easy or difficult to generalize to? And again, so the motivation was exactly these kind of things where we wanted to understand what makes generalization hard. And also here's another thing that we were very curious about. So we saw this phenomena where given some utterance in the semantic parsing setting, we saw that 4 different models that were trained on some compositional split failed to produce exactly the same token, which is here exists. And we see that they all fail in some different ways, but all of them at the same exact position. And this is something that kind of hinted us of where the problem of the generalization here in this instance. So I will get back to this example, but first let me tell you about the setup that we used. So basically, we chose data sets for which a random IID split yields high model accuracy. So we took COVR, which is a semantic parsing version of the data set that I've just shown, overnight, schema 2QA, and eddies. And for each one of these data sets, we've created multiple compositional splits. And then what we did, and this is like a behind the scenes frame, we basically just manually looked at all of these results from different splits. And we tried to distinguish between these examples that models could answer very well on, where maybe all of the models got right, and to try and understand what's different from these examples to the examples that all models failed. And we got to this main observation that a test instance is hard if it contains a local structure that was not observed at training time. So, for example, what is a local structure? So you can see here that we have this structure of a parent and child operators in this program tree. And if this specific structure, which is local, since it's a parent and a child, which are adjacent, if these were unseen during training time, then this example is likely to be hard. However, if we take a structure which is not local, such as a grandparent and a grandchild, then this is more likely to be an easy example. I mean, if this structure was not seen during training time. So I'm going to define this a bit better next, but note that the input here is a string, but actually what matters is the tree structure, which is actually kind of nice because it shows, I mean, these are just regular sequence-to-sequence models, and it shows that these models, and specifically the decoder, has some has a good notion of the tree structure, actually. Okay, so what is a local structure? I will show this pretty quick. So you have some program. You can deterministically parse it into the program tree, where we have both parent-child relations and adjacent siblings relations. And then a local structure of size 2 will be all of the parent and child and all of the siblings. And we define something very similar to local structures of size 3 and 4. And now, so let's define our decision rule. So our decision rule is some way to predict the easiness of the example. So I've talked before about predicting how difficult it is. So this is just the opposite. It makes things a bit simpler. So given some program of a test instance, as we see here in this example, basically what I've said before is that you just have to look at these unobserved structures. And if you have any unobserved structure, that is structure that was not seen during training time, then this will be a hard example. But in fact, we even this very simple rule actually isn't too bad. But we make things a bit more or a bit less brittle. And we actually also have a look at the structures that were observed. Because maybe, for example, find cat is so similar to find dog that even though it wasn't observed during training time, then if find dog is very similar and it was seen during training time, then it won't be that hard to generalize to find cat. So we define this function that I'm going to go over, where basically we look at the similarity of every unobserved structure with the observed structures. So I'm not going to talk about it, but we use this very simple similarity function that just compares different contexts that these tokens were seen with. And here we see that indeed find cat is 90% similar to find dog. So it's 35% similar to find filter. And exist doesn't have any structure that it's very similar to. So it has this 20% similarity to and equal. And then we take for each of these unobserved structure, we take the maximum. And this actually can represent the easiness of the structure. So we can see that find cat is 90% easy in a way, which makes sense because we've seen a very similar structure in the training set. However, and exist is something that will not be easy to generalize to. And then we just take the minimum out of all of the structure, which in this case is 20%. Okay, any questions so far? Okay, so let's see how well does this work on predicting the easiness. So basically, recall that we have trained 4 models on a lot of different splits from different data sets. So basically, we have the gold easiness of these models on each one of the example, where the gold easiness is just the majority. If we take the 4 exact match accuracies for each of the example, then we take the majority to determine if it's easy or difficult. We discard examples where there is no majority. This didn't really happen a lot. And finally, so we have these gold labels, which are 0 or 1, and we can now evaluate our classifier, our easiness prediction, which yields some result between 0 to 1. And since this is a binary classification task, we can evaluate our easiness classifier with the area under the curve, the AUC metric. And we see here that we get really, I would say, good results. So especially on the synthetic data set, we get to 90% in 2 of these cases, which really show that this decision will works and that models have a hard time to generalize to unseen structures, but also in the natural data sets that have natural language. So this classifier is able to predict very well. But of course, in a natural language setup, you will still have there are other reasons for examples to be hard, so it makes sense that the result here will be a bit lower. And so I won't have time to go over the baseline adaptations, but basically we show that if we change a bit the definition of the decision rule or of the local structures, then scores are in general lower. Okay, so now we can get back to this example that we've seen where all models are wrong at exactly the same place. And now, given this insight about unseen local structures, it's easy to tell that the reason is that there was some unobserved local structure. In this case, it was or and exist. And we see here that indeed all of the models are just wrong at this location. Okay. And finally, you might wonder if this is something that is specific to transformer decoders. And we also test this with LSTMs, and we show that we get more or less the same results, slightly lower, but still showing that LSTM decoders have the same problem with unseen local structures. Okay, so how can we leverage this fact to improve generalization? So we show this very simple way where, given a training budget, so this setup where you have a training budget is realistic in the setups where, for example, you have synthetic data or augmented data and you have maybe millions of examples, so you don't want to use them all. So we show that if you just choose your training examples such that they maximize local structure diversity, then we get results which are better on compositional splits than just uniformly sampling examples.
And there's a question from Matt.
Yeah, sure.
There's a quick question. So earlier you mentioned that for some splits, the models do tend to generalize. Does this unseen structure explain why those ones would be easier for the model to generalize to, or is that? Yeah, I'm just wondering if it's able to explain that.
Yeah, okay. So that's basically what we're measuring here. I don't know, maybe it's not. We did have some metrics which just measure at the split level, and we saw that in all, like for example, in the synthetic cover data set, for which we had over 100 splits, then we could really almost perfectly predict which splits will be hard or not. There were some unexplained cases which we really couldn't tell what's going on there, but yeah, in most of the cases this explains. And for the natural language splits, then there are definitely some other causes except the decoding part. So there it works in many cases, but definitely not at all of them.
Okay, thanks.
Okay, so yeah, one last thing I will say about it. So we saw that models overfit to local structures, and we talked about this in the context of semantic parsing. So I want to say just this general thought that this might not be just specific to semantic parsing. And if we look at the more general case of language modeling, we have, so I've seen this paper from McCoy et al., the Raven paper from last year, and they measure, so the y-axis here is the proportion of n-grams that are novel, and the x-axis is the size of the n-gram. And we can see that when the n-gram size is small, then all of the different models that they tested with has a lower proportion of novel n-grams than the baseline, which is what humans would write. And for the large size of n-grams, then this is the opposite. So again, this shows that it seems to be some inherent problem with the coders, which are not very, which kind of overfit to the structures or n-grams that they've seen during training time, and it's harder for these models to generalize to novel structures or n-grams. Okay, so we've talked about how we can fine-tune pre-trained models and about the limitations that we see there. And finally, let's talk about large language models that we don't fine-tune. So of course, we know that these models have, in many cases, remarkable generalization abilities. So we can ask this question, do large language models solve our problem? So here's the accuracy on COVR 10, which is synthetic. But we see kind of the same phenomena on non-synthetic data. So we see here that GPT-3 Da Vinci 2 actually generalizes better than the 4 of the models that we experimented with. And remember that these 4 models were fine-tuned on this data, but the GPT-3, we just uniformly selected examples for the prompt. And it already has this almost 10% boost. However, if you look at an IID split, you see that GPT-3 is actually is not as perfect as the other models. So again, this is a synthetic data set. So of course, the models can get to a pretty much perfect accuracy. But even in this synthetic data set, so GPT-3 could not generalize in the IID split. So the answer is not straightforward. So compositional gap is indeed smaller for larger language models, but it's far from perfect, and IID performance can even be lower.
Ben, just quickly, so
Yeah.
your T5 and BART are fine-tuned, and you're comparing them to GPT-3. So GPT-3 is your large language model, T5 large is.
Yeah. So the first 4 are fine-tuned, and the only GPT-3 is we use in-context learning. Okay, and what about scaling? So what if we, how do the different OpenAI models perform? So we see here that scaling is important. So the 3 smaller versions of GPT-3 did not yield any correct answer. And recall that this is a synthetic data set. So there's even no natural language generalization that it should do. But actually, it's not just about the scaling of the number of parameters, since the difference between Da Vinci 1 and Da Vinci 2 is actually not the number of parameters, but just the data that it was trained on. So this shows that it's not just the parameter size, but also the data that we were training on. And unfortunately, there's nothing very scientific to say about this specific difference, since we don't have access to the data difference between Da Vinci 1 and Da Vinci 2. But still, this shows some interesting directions that we can follow. And so, okay, so now next, what can we do? Since we've seen, since now we can fine-tune it. So basically, most of the thing that we can control is the in-context samples that we select. So this is definitely something that we can improve, since the score that I've shown before is just a uniform sample of examples from the training set. So what happens if we use BM25 to select examples that are most similar? So in this case, it's actually worse than just uniformly sampling. And the reason is that diversity in this case is important. If you just take, I didn't write. I'm not sure if this was an Oracle. Oh, actually, it doesn't really matter. It's in a synthetic data set. So even in an Oracle setup, the BM25 got worse results. And what we suspect is that the reason is the lack of diversity. So if the model just sees questions which are really similar to one another, then it will still have problem to generalize to unseen compositions. So instead, what we can do is to try and cover all of the different atoms that are in this that are contained in this test example. So we can use an oracle that will tell us which atoms we have, and then we select examples that are that cover as much of these atoms as possible. And these are the examples that we select in for the prompt. And we see that now we gain a very large increase in performance of about a bit more than 20%, 20 points. And this works also if we don't use an oracle setup, but we try to predict these atoms. And we do this, so I will not talk too much about it, but basically we do this in a two-phase setup where we use another model just to predict the atoms. And this is something that we're still currently working on, so I don't have like final results on other data sets, etc. But it's also something I'll be very happy to talk about. And finally, some other things that we can do. And again, this is in very preliminary stages, and I would love to talk about this with people. So some thoughts of what we can do, since we can't fine-tuning, can do fine-tuning, is multitasking, where basically you can, so suppose you have a model that you can fine-tune, but you do this on examples which, if you have the data set that you care about, you use other data sets for which you have compositional splits, and basically you do some kind of meta learning to let the model learn how to do this kind of compositional splits. And one other direction that we're exploring is to use a large language model that we've seen that can generalize and don't have this unseen structures problem as much as fine-tuned models. And we can use these to augment data and then possibly use this data to fine-tune smaller models. And again, if this is something that people find interesting, I'll be happy to talk about and possibly collaborate. Okay, so let's do this recap of the things and think about what we can do to improve compositional generalization. So we talked about specialized architectures, which may, where basically we've seen that we can use this to improve generalization. But I guess if I would work on a specialized architecture these days, I would try to make models more general, in the sense that I think that they must be pre-trained in a way so that we can use this in a more general setup and for more general NLP tasks. And about this fine-tuning paradigm, basically we've seen that the problem is, or at least one major problem is with overfitting to scene structures. And one way to overcome this, that actually there are a few papers from recent years that do this, is augmentation. And I guess if you understand these local structures, then augmentation makes a lot of sense, because when you create augmentation, basically you let the model see more local structures, so the model is less likely to overfit. One other direction is grounding. So suppose your model is grounded to some external knowledge graph or other modalities, then again it might be less prone to overfit to these structures, since it won't have to just decode such it won't have to do this decoding just from this enormous size of parameters, but basically it can just use this grounding that it has access to in order to be able to better predict what should come next. And finally, another thing that I would expect to work well or to improve generalization is decomposing the problem into smaller problems. And I know this is something that a lot of people here have been working on, and I think it will be very nice to try this in compositional generalization setups, as we can assume that models that can do this decomposition very well will have less of this generalization issue with, for example, with scene structures. Okay, and finally, how can we improve large language models which we don't fine-tune? So this is something that we've talked about in the last slide, where basically we want to improve both the IID and the compositional split generalization. So things that we can do is to optimize our prompts and our retrieval of the examples that we show in the prompt. We can do this kind of meta learning where we multitask different compositional skills. And as we talked about, we can augment these large language models and then use these examples to fine-tune smaller models. And yeah, so that's it. So thank you for listening, and thanks to my collaborators over the last few years. And that's it. So I'll be happy to answer any questions. Thanks.
Sven, I think we have 6-7 minutes for questions.
Yeah.
Because I can start off with one for the because trying to tie your second and third part of the talk. And so in the second, you found that unobserved local structures make it hard.
Mm-hmm.
The third one, so I guess 2 questions. Is it true that that's also a problem for large language models that are not fine-tuned? And if so, would putting some of them in the context help? I know you're putting atoms, and there's not a lot of space to put all local structures or all binary structures. But that,
So you're asking what if we put local structures in the prompt?
yeah, some local structures is binary label.
Yeah, so this is something we're actually experimenting with. I mean, there is a question of select. Yeah, as you said, you can't put all of the local structures in the prompt, so you still need to find some way to pick these local structures. And we have seen that if you use an Oracle setup to pick these local structures, then you do get some gains actually. But it's not really, since different from atoms, there are a lot of local structures, and it's hard to pick them right. So it's kind of an open question, I'd say.
And what happens, just a follow-up, what happens if you were to able to fine-tune GPT-3 on a small subset of those structures?
Yeah, that's an excellent question, which I'm curious about. We haven't done this. I would expect that if you fine-tune these large language models, then we will still see this problem of overfitting. And yeah, this is something that I hope to maybe check in the near future.
Okay.
And Ben, when you mention observed local structures, how many times do you have to see it for it to be observed? Is it just once, or and does the number of times you've seen it make a difference?
Yeah, that's a good question. So in our case, it's kind of a binary decision. If we see it once, then we consider that it's seen. But that's definitely not the case. Like in real setups, we have seen that if it's just seen once, then it's not enough. But we don't model this in our case, and it's definitely something that has an impact.
Because a quick follow-up on that, you have this equation with min f max. Instead of max, you could think of some aggregation. Like if this, maybe the exact thing has not been seen, so max is low, but you have seen many things similar to it, like find cat, find dog, find block, find this.
Yeah.
20 of them, you can probably do the 21st.
Yeah, I agree. So I definitely think that you can improve this decision rule. It's just, we were kind of happy that we had this very simple decision rule, and even this simple rule kind of explained a lot. But so it was by design simple, but definitely you can make it better.
Did you calibrate the similarity function you used there, or was it just off the shelf?
Yeah, we did some. We tried some few different variations of it. Yeah.
Is it a lexical similarity? It's like find cat and find dog. Is there a structure?
Oh no. It's just okay. I won't find it. But basically, you just look at the of the different contexts that these tokens are seen to the left and to the right. You just compare it you compare the sets of these contexts.
I had sort of an open-ended thing. So in the first part, you had like some really excellent work that you did in the first part of your talk. Is there any hope of using any of those intuitions into the third part? Like, can you do, over-generate using GPT-3 and then have your scoring mechanism of scoring those structures? And so like do this at the decoding time basically rather than training time.
Wait, do you mean like which kind of way are you using GPT-3 to create the structures or to create?
So can you use GPT-3 to build upon simpler parts and then build it up to eventually have a structure?
Yeah, I agree. This is something that I think will be interesting to try. So it's related to the decomposing the problem that we've talked about. So I do have this. I mean, I do think that you can definitely use GPT-3, for example, to decompose the problem, and maybe then you can even use this as data to fine tune some smaller models. This is again something I find really interesting.
Have you tried this sort of modern chain of thought, or just suggest to GPT-3, let's decompose the model, this problem, and then let it solve it, and then see if it does better.
Again, so this is something we've thought about, but we didn't try it yet. Yeah.
I guess building on top of that, do you have a suggestion for what to do for cases where you do not know the structure? Like how would you select examples, or I guess your hypothesis is that structure has a lot to do with generalization. So in the absence of structure, is there anything we can do?
What do you mean in the absence of structure?
Like if I do not know what the semantic parse is, or I don't know what the underlying tree structure is for a problem, like the drop data set, for example. You have questions and answers. You do not know the underlying structure for the questions. How would you kind of select examples?
Do you mean in a task where the output is just an answer, so we don't have structure? Oh, okay. So so we mainly focused on problems where we do decode some some structure, and so about the encoding. So I'm still very curious about. So I know that Matthew here had this project where he test. You also on that paper, right, with the regex classifier of trying to solve this regex problem, and so there you only had an encoder, and you also tried. I've seen this unseen local structure prediction, and it didn't work. So I would say that definitely something else is going on when you just do this encoding.
Got it. So maybe there's a different theory of compositional generalization when you talk about just answering instead of structured prediction.
Yeah, definitely it could be.
Okay, I guess we are